welcome to this third session of Newton's laws of motion. Let's begin with a quick recap. So last time we were discussing about the fundamental forces known in nature, and we saw that the fundamental forces the four types of fundamental forces known to physics consist of gravitational force, so let's discuss a little bit more about gravitational force today. So gravitational force, the most fundamental form of gravitational force, is given by the universal law of gravitation. According to which, if you have two particles, M1 and M2, which are placed at a distance r, any two particles, they might be very light particles like 2 electrons, or they might be considerably heavier particles like you might be considering 2 planets. So this is the force on particle 1 because of particle 2, and this is the force on particle 2 because of particle 1. So first of all, you can see over here that the force on particle 2 due to particle 1 is equal and opposite to the force on particle 1 due to particle 2. This is in agreement with Newton's third law, that every action has an equal and opposite reaction. But now more importantly, the magnitude of this force, which equals the magnitude of this force, is proportional to product of masses and inversely proportional to square of distance. Okay? In fact, this magnitude of force is given by this very famous equation, where capital G is called the universal gravitational constant. And its approximate value is 6.67 into 10 raised power minus 11 Newton meter square per kilogram square. Okay, so this is just right now it's more in terms of general information. We will be studying this in much more detail, this universal law of gravitation. We'll be studying this in a lot of detail in the chapter of gravitation. So it's not that you have to memorize this right now, it's just to give you an idea. So what you will realize when you look at this formula is that this constant is an incredibly small number, 10 raised power minus 11. So that means for the force between two particles to be significant, the masses have to be extremely heavy and the distance has to be comparatively less, because r square is in the denominator. So obviously the closer you bring the particles, the heavier, the more the magnitude of the attraction force, the gravitational attraction force. So, but at the same time, it's proportional to the product of the masses also. So because this constant is of the order of 10 raised power minus 11, for this force to be a significant amount, at least one of the two masses has to be very heavy. So that is why, for example, on the surface of the earth, we don't really take into account the gravitational force of one body on another. Like let's say we have two blocks that are lying at a distance of 5 meters or something, or even much closer, like 5 centimeters, but their masses are in kgs. So you will see that the force between them is negligible. But at the same time, the significant gravitational force on the Earth's surface is the Earth's gravitational force on any other body, because the Earth's mass is extremely heavy. So this force becomes very significant for the Earth because the mass of the Earth is very heavy. So that brings me to the second point about Newton's law of gravitation, or the universal gravitational law. So that is that if we consider, instead of two particles, one of the objects which has mass is a spherical body. we have a sphere of mass m and radius r, and we have another particle of mass small m, such that the distance from the center of the sphere to that particular particle, that distance is some r again. So center of the sphere to that particle's distance is r. So now we want to look at the interactive force between, rather than two particles, one of them is a spherical body and the other one is a particle or a point mass. So as it turns out, that there's no difference in the formula whatsoever. The amount of force is exactly the same as the force between two particles, only now the direction of this becomes like this. And the direction of the force on this one same type of expression for force. Equal and opposite forces acting on both of them. So that F is G capital M into small m divided by R square. Okay. And another version of this is if the particle happens to be on the surface of the sphere. If it so happens that, so this is now like, for example, what happens in the case of Earth and any body lying on the Earth. So if the particle is right against the sphere, right at the surface, the sphere has a radius capital R, mass capital M. Then again they experience mutual attraction. This time the force becomes G into product of masses divided by radius square. So for example, when we are talking about weight of any body on the Earth's surface, this is the force we are talking about. Only capital M. So from this you can understand that weight of a body mass M on the Earth's surface. So take mass of the Earth as, let's say, ME, and radius of the Earth as RE. So what we commonly know as the M into acceleration due to gravity, that is actually G into product of mass of Earth and mass of the body divided by radius of the Earth square. This is what we call the feet. And therefore, the acceleration due to gravity on the Earth's surface is in fact given by this formula. And when we substitute the approximate values of mass of Earth and radius of the Earth in this, we get it approximately 9.8 meters per second. So as I told you, as of now, this is general information. You don't have to really memorize this information. This will become significant in the chapter of gravitation, where of course you'll have to remember all these formulae, this concept. But this is just to give you an idea about one of the four fundamental forces, which is the force of gravitation. So this is the type of force that acts between two particles, and that is extrapolated into the force acting between the gravitational attraction between a sphere and a particle. Whether the particle is somewhere quite far away from the sphere center, or it's right at the surface of the sphere, the principle, the basic nature of the force has a similar relationship. So this just gives you a bit more idea about the concept of weight of an object. The weight of an object is actually an interactive force between the Earth's mass and that particular object. And the action-reaction pair, for that gravitational interaction is this. Just as the earth pulls down an object, what we mean by down is standing on the surface of the earth, the horizontal plane is the tangent plane at that point. So the vertical line becomes nothing but this line, this radial line. So this direction of the force, which is towards the center of the earth, from the surface of the earth, it will look like a vertically downward force. Similarly, if we talk about the second fundamental type of force, which is the electromagnetic forces. Yes, definitely. It's direct. I use the gravitational attraction is directly proportional to product of the masses. So that is why, for example, if you take the same object to the surface of a planet which has more mass than Earth, but same radius, it will experience more weight. The mass of a particular planet is more than the mass of the Earth, but the radius is the same. It will experience more gravitational force. On the other hand, if you take it to a planet of same mass, but radius is larger, then it will experience less force because it's inversely proportional to r square. Similarly, the force is also proportional to the mass of the object. So if you compare two objects on the surface of the earth, the lighter object or the one having less mass will experience less weight. Okay, good. So, IITians, okay, I'll send you the notes so you can see the exact formula and all that later. So, as I said, this is, you don't have to really 100% memorize this formula and all this right now. You just need to have a general idea so that you understand better about weight. In this chapter, Newton's law of gravitation, Newton's laws of motion, we will always understand the weight as this simple formula. It's m into small g, where g is 9.8 or approximately 10 meters per second square, and the direction of it is always vertically downwards. So weight of an object on the Earth's surface, it always has a magnitude of mg and acts vertically downwards. What in the context of the above diagram is towards the force vector is towards Earth's center. The direction of the force vector or the weight of an object is pointed towards the center of the earth. So that is what from the surface of the earth it becomes vertically downwards. So that's the only thing we need to remember. Now moving on about electromagnetic forces. So this is divided into two categories, electromagnetic forces. So basically the general definition of electromagnetic forces is it is the interaction between charges or charged particles. As you know, charge is again a fundamental property of physics, which comes with the fundamental subatomic particles of electron and proton. They have opposite type of charge, and protons, as you might have heard, consists of quarks. So if you break down a proton into quarks, then the property of charge is lost. And on the other hand, the electron is a significantly smaller particle compared to the proton, and electron is yet to be split in physics. Okay, so we don't know what we'll get when you split an electron. However, the property of charge is lost at the electron level. It's understood that if you were to split the electron, the property of charge would be lost. So the fundamental particles of physics which have this property of charge are nothing but electrons and protons, and thereby if we say any body or any object has a certain amount of charge, it is because there is an imbalance between the number of electrons and protons within that body. So typically protons are very difficult to displace from a material because they are located inside the nucleus and they are bound together by very strong forces, which are called the strong forces or nuclear forces. So it's not really possible to remove the protons from a material in order to charge a material negatively. So typically what happens is when a material or a body or an object is charged, we are manipulating the electrons, and that too which electrons? The electrons that would be present in the outer orbits in its atoms, because those are the ones which are easy to manipulate. Okay, so anytime a body is actually having negative charge is because somehow you have supplied excess of electrons to the body. Similarly, anytime a body is positively charged, it's because by some mechanism you have removed some of the electrons from the body. In principle, we are never really able to manipulate the number of protons within a material because they are very deeply set and they are bound by very strong forces within the nuclei. Okay. So now coming back to this electromagnetic forces, the first category of electromagnetic forces is what we call electrostatic force. Which is something we'll study in a lot of detail in the first chapter of class 12, which will be electrostatics. So as the name suggests, static का मतलब क्या होता है? Rest. So this is the interaction between particles, charged particles at rest, or in static state. Okay. So they interact with each other with a type of interaction which is called electrostatic interaction or electrostatic force. And interestingly, that force is very similar to the force of gravitation. Only difference is that, for example, if I have two positive charges, plus Q1 and plus Q2, then instead of attraction, they will be repelling each other. So if I have two positive charges Q1, Q2 at a distance R, then they will be repelling each other such that this will experience a force going directly away from Q1. This is the force on to due to 1. And similarly, this will experience an equal and opposite force. So again, this follows the principle of Newton's second law, that the action has an equal and opposite reaction. So F21 happens to be minus of F1, equal in magnitude, opposite in direction. They are an action-reaction pair. Now, the magnitude of this force is given by a formula. This is why I said it's similar to Newton's law of gravitation. It's proportional to product of the magnitude of the charges and inversely proportional to the square of the distance. So this particular principle is called Coulomb's law. And here the constant key is 9 into 10 raised by 9 Newton meter square per Coulomb square. So Q1 and Q2 are charge in coulombs. SI unit of charge is coulombs, as you know. R is distance in meters, and obviously F is force in newtons. Yeah, Yashwardhan, you don't need to write all this in detail. You just need to understand this. Okay, you will have these notes. Don't worry. So this is electrostatic force. It is the force between charges at rest. Now, similarly, electrostatic force can also be attractive, as you know. The force can also be, on the other hand, if the charges are opposite in nature. That is, one of the charges is, let's say, positive, and the other charge Q2 is negative. Then you know that they will be applying a attractive force on each other. But even that attractive force's magnitude will be given by the same formula. K into magnitude of product of charges divided by square of distance. Now the other type of interaction between charged particles is what we call the magnetic interaction. So magnetism or magnetic interaction this is the between moving charges. So for example, it's an experimental law that if I have a charge positive q1 which is moving in this direction with a velocity v1, let's say, okay, and I have another charge particle plus q2 which is moving parallel to this one but with a velocity v2. Then what happens is they experience attractive forces. Or similarly, another example of this is if I have a current carrying wire. So current carrying wire is also a stream of moving charge. So if I have a current carrying wire like this and somewhere near this, if I were to project a particle which is having positive charge with some velocity like this, then this will happen to experience a magnetic force because of this current or because of this stream of moving charges, which will happen to be in this sort of direction. Happen to be in this sort of direction. Or for that matter, if I have two current carrying wires only, but they are carrying current parallelly. That is, they are carrying current along parallel lines. Then they happen to experience attractive force with respect to each other. They tend to attract each other. Okay. Or if you have two currents going in anti-parallel directions, you have two current carrying wires. This carrying current I1, let's say like this, and this carrying current I2 like this, let's say. Just a moment, guys. We have this kind of situation. They experience repulsion force, but now all these forces are magnetic forces. All these are examples of magnetic forces. These are between moving charges. And of course, you know that magnets also apply magnetic force on each other, or a moving charge in the vicinity of a magnet, or a current carrying wire in the vicinity of a magnet will also experience magnetic force. Okay. So again, what happens inside a magnet is that you have electrons which are in orbital motion, and they are basically causing a situation of magnetic field, or they are behaving in the same way as these physically moving charges or these streams of current. Yeah, because moving charge creates magnetic field. Just like current creates magnetic field. Now, current is a stream of moving charges, Ayush. So that's why a charged particle with motion or having certain velocity creates something called magnetic field. And another charged particle moving inside a magnetic field experiences magnetic force. Okay. So again, I won't get into too much detail over here because we'll study about this in more detail in class 12th. Between moving charges. It's example of magnetic force between moving charges. No, charged particles at rest do not experience magnetic force. Okay. So that is the important thing over here. Magnetism is the interaction between moving charges. So a charge at rest does not experience magnetic force. Yes, so a moving charge creates magnetic field, and a magnetic field applies force also on a moving charge. Similarly, a current creates a magnetic field. Now, you would have seen that experiment in your class 9th or 10th, where you can measure the magnetic field lines. They are forming concentric circles or closed loops like this around a current carrying wire. Yeah, if the car has some net charge with us, then it will generate magnetic field. Or more importantly, if a charge body is moving inside a magnetic field, it will experience magnetic force. That is a principle on which bullet trains run, Hitansh. To answer your question, bullet trains run on the principle that they have something called magnetic levitation. So because of their motion, they experience magnetic force in a direction which is opposite gravity. So they are actually lifted a little bit compared from their rails, and that minimizes the frictions. Yes, magnetic levitation, maglev's friction. That is the correct. Okay. So more about that in class 12. So collectively, electrostatic force, that is the force of an interaction between static charges, and magnetic force, that is the force of interaction between moving charges or currents. Okay. They are called electromagnetic forces, and that's the second fundamental type of force. The third fundamental type of force, as we were talking about, is the strong or nuclear forces. So now this comes into a domain where things are not that well known in physics compared to electrostatics or magnetism or gravitation. So we don't have a clear-cut formula for nuclear, but we have certain information or certain certain characteristics about nuclear forces through experiments. Okay, so what are nuclear forces? Nuclear forces are very strong attraction forces between subatomic particles of the nucleus. So namely, the subatomic particles of the nucleus, the significant ones which experience nuclear forces of attraction are protons and neutrons. So this can be an interaction between proton-proton or proton-neutron or neutron-neutron. Now, one of the things which is known about nuclear forces is that they are very short range. That's why they are also called short range forces sometimes. What that means is that the nuclear force is of very large magnitude when the particles, that is proton, neutron, etc., are at distances which have order of magnitude of Fermi. One Fermi is equal to 10 raised power minus 15 meters. Okay. But the nuclear force are negligible at larger distances. And what we mean by larger distance here is larger compared to this. So for example, at a distance of the order of magnitude of even Armstrong, where 1 Armstrong is 10 raised by minus 10 meters. So actually it's a very small distance, but compared to Fermi, it becomes a large distance. So even at a distance of the order of magnitude of Armstrong, nuclear force is negligible. Now what is the significance of Fermi and Armstrong? The significance of Fermi is that nuclear diameter or size of the nucleus is of the order of Fermi, whereas atomic diameter or atomic size is of the order of Armstrongs. So yes, another important thing is that nuclear forces is independent of charge, does not depend on charge. And finally, one more significant point about nuclear force. It is the force that is responsible for binding the nucleus together. Okay. So, nuclear attractive force is responsible for what we call the binding together of nuclear particles. So it is responsible for, or nuclear attractive force, you can say, is responsible for what we call binding energy of a nucleus. So this is a very huge amount of energy. So for example, any nuclear reaction like radioactive decay of nuclei or fission nuclear reactions, for example, which happen in the sun or any star. The release of nuclear energy that happens in this kind of thing, any nuclear reaction, the release of tremendous energy, that is nothing but binding energy. Or nuclear energy. Small correction, this typical stars, they have fusion nuclear reactions, not fission nuclear reactions. Fission nuclear reactions happen in nuclear reactors. Another example of this is that so the evidence that nuclear force is very strong is from the fact that nuclear energy is tremendous. So for example, in a nuclear reactor or a nuclear power generator, you need very small amount of nuclear fuel to generate a very, very tremendous amount of energy. So why that happens is that the amount of energy released from the binding energy of the nucleus is much, much more significant compared to electromagnetic energy. So for example, if you compare a DC dynamo okay, or a hydroelectric turbine with a nuclear reactor. So the amount of energy that you are getting from those kind of reactors, like a hydroelectric hydroelectric turbine or a dynamo or something like that, is much less compared to the kind of energy that you're getting from a very small amount of nuclear material undergoing a nuclear reaction in a nuclear reactor. So the reason for that is that the binding energy of a nucleus is a very tremendous amount of energy compared to any type of electromagnetic energy. So this is one example of how in our everyday lives we experience the power of nuclear forces, the tremendous nature of nuclear forces and the tremendous amount of binding energy associated with the nuclear forces. Now, our very sustenance depends on the energy supplied by the sun, and what is responsible for the sun to be able to emit this energy? It is nothing but nuclear forces and nuclear interaction. At the core of the sun, the nuclei of lighter types of atoms like hydrogen, helium, etc. are undergoing what is called fusion reactions, where they fuse into heavier nuclei, and as a result of that, they emit tremendous amount of energy. Now that energy is nothing but nuclear energy that is coming from the nature of nuclear force or the interaction of nuclear force between subatomic particles inside the nucleus. So that's something which is very fundamental to our existence on Earth. The solar energy which is experienced on the Earth. Now that is coming from which of the fundamental interactions in nature or in the physical universe? It is coming from the nuclear one, or what is called the strong interactions. Okay, so other than this, we won't get too much into nuclear forces in our study in 11th, 12th physics. Nuclear force you will be able to study in much more detail if you do graduate level physics, or you get into a branch of engineering which has elements of nuclear power related to it. Okay. Both are controllable. Okay. How you control it is on the basis of how we use inhibitors, etc. Because typically both fusion and fission reactions, Manas, are what we call chain reactions. So unless we have inhibitors present, we are not able to control it. So it's a very complex process trying to control the amount of energy liberated in a chain nuclear reaction. But yes, typically we say that the fusion reactions result in more energy compared to fission reactions, which is why you would have heard that hydrogen bombs are much more dangerous compared to the normal atomic bombs which are based on fission. Alright. Yes, Ayush, that's a correct statement. Haripriya, it's okay. You can go through the notes later. You can magnify it and go through it. This is just to give you an idea about this. What we're discussing is more important than the notes exactly right now that I've written. In fact, you can read more about nuclear forces if you like on the internet or in reference books, etc. At this stage, we don't need to know more about nuclear forces. In fact, as I was telling you last time, as far as mechanics is concerned and our everyday, mechanical world around us, the significant type of forces at the fundamental level are the first two, the gravitational and the electromagnetic interactions. Okay. Now, just to complete the story here, the fourth and final type of force is what we call the weak forces or electroweak forces. So we can control fusion reactions also. If there was no way to control it, then how we would create a reactor? Because we need a controlled reaction, which is emitting a controlled amount of power. So Aditya, the whole idea of a nuclear reactor is to have a controlled chain reaction, controlled chain nuclear reaction. If it is not controlled, it will be a very dangerous situation. It will be more like an atomic bomb rather than a reactor, which is destructive rather than being something productive. Okay, now so a leakage means that situation when the inhibition of the chain reaction is somehow getting suppressed. So there is much more energy liberated than what the reactor was designed for. So there's leakage of energy, leakage of radiation which is happening from the core of the reactor. And Chernobyl was the most dangerous such accident in the history of nuclear power. So as you know, exposure to radiation causes widespread damage to life. So that is why it is very, very important to control and inhibit a nuclear reaction within any nuclear reactor's core. Because the core is designed to be able to suppress a certain amount of energy from coming outside the core. So if more than that is generated, then there is leakage and that causes widespread damage. So hope you are understanding this point. Because it is not that efficient in inhibiting nuclear reactions. Okay, man. Okay, now the fourth type of force is called the weak interactions, or also called electroweak forces. Now, this is an area which is of fundamental research in physics. This is the area of particle physics. You might have heard the branch of physics called particle physics. Okay. Or it is sometimes also called high energy physics. Where you have experimental high energy physics in which you have what is called particle accelerators, like the CERN Labs particle accelerator. So what is done in this is, so what are weak forces, weak or electroweak forces or interaction? It is the interactions between subnuclear particles, or what is called the fundamental particles of physics. Okay. So quarks, leptons, electrons, positrons, which is the antiparticle of electrons, neutrinos, okay, Higgs boson, which is, so these type of particles, they interact via electroweak forces. Okay. And these interactions are studied through collision experiments. In particle accelerators. Okay. So this is again more about your general knowledge. We won't be studying any part of electroweak forces. We won't be doing any discussion about electroweak forces or weak interactions at 11th-12th level physics. In fact, this is an area of research in physics. So you won't really be getting into it before you study at the PhD level or postgraduate level in physics. Okay. Yeah, so see, Harpriya and others, this is going beyond our scope over here. Okay, so I will not discuss more about what is neutrinos, what are Higgs bosons, etc. These are things that you can search about and find out yourself, but that is for your general knowledge. It is just for the sake of completeness that I am telling you what the fourth type of interaction is. Okay. Yeah, uncertainty principle applies to this. Positron is the antiparticle of electron. So yes, antimatter also applies over here. Okay. Yeah, and when you talk about weak forces or electroweak forces, you are getting into the domain of particle physics. So Ayush, you're correct in saying that uncertainty principle, Heisenberg's uncertainty principle, plays a big role in understanding these interactions. Okay. But I'm sure many of you, most of you would have heard about particle accelerators. You know, those giant circular kind of tunnels in which we use magnets and electric fields to accelerate subnuclear particles to incredibly high speeds. Yeah, mesons, pi mesons, they are also examples of subnuclear particles. So these particles are accelerated to speeds very close to the speed of light. Okay, so as you know, no particle can actually achieve the speed of light, but given a very high amount of energy, they can be accelerated to something very close to the speed of light. And at that kind of energy or that kind of very high velocity, if they are smashed against each other, if they are made to collide against each other, then that collision reaction results in the production of more subatomic particles, so subnuclear particles. And that is how these fundamental particles of physics are discovered. So the whole game of high energy physics is that your technology has to keep producing accelerators which can be used to accelerate these particles to higher and higher velocity, which will give access to experiments where more and more fundamental particles of physics will be generated during the collisions. So it is like you are trying to discover what are the particles available at the fundamental level by creating such particles in these collision experiments. So it becomes a huge constraint of technology that how you are able to deliver that much energy to the accelerated particles so that they will have the required amount of collision energy and they'll be able to generate the fundamental particles of nature. So, you know, in the papers, you would keep reading about things like Higgs boson, God particle, you know, fermions, etc., which people are trying to discover or confirm the existence of through these collision experiments. To a certain extent, yes, these particles are time travelers also because they exist for very short duration of time and they are traveling at such a high velocity that they undergo an effect which is called relativistic effect. So at such a high velocity, that particle's understanding of time or that particle's relationship with the universe around it in terms of time is dilated compared to the Earth's reference frame of time or human beings' reference frame of time. So yes, they do become time travelers in that sense to a certain extent. Yes, mass is affected definitely. So the principle of relativity, Ayush, tells us that at very high velocities, the mass also significantly increases. So that is called the concept of dynamic mass, which is one of the cornerstones of the principle of relativity also. That mass is actually a dynamic quantity. But that happens at very high velocity. Okay? It doesn't happen at the kind of velocity that we talk about in the mechanical world around us. Okay. So these are some general aspects to know about, you know, weak interactions, and it's just for your own interest. You can use these, pick up these words and search more about them yourself and find out more at a general knowledge level. But as I said, they will not play a role in our physics syllabus. Now coming back to our physics syllabus. Now coming back to the chapter of Newton's laws and mechanics, now you will see that the common mechanical forces in what we call Newtonian mechanics, that is a mechanics in which we apply Newtonian laws or Newton's laws of motion. That kind of mechanics is called Newtonian mechanics. So the common mechanical forces that we experience in Newtonian mechanics or systems, mechanical systems where Newton's laws are applied, they are things like weight, okay, contact forces, which include both normal reaction and friction. Then things like tension or tensile force. Okay. it acts along a rope or a thread or a chain. Okay, these kind of forces. These kind of normal mechanical forces that we talk about, these are always either gravitational, which is the weight one, or electromagnetic in nature. Contact forces, tension, etc. These type of forces that we experience in Newtonian systems or Newtonian mechanics, at the fundamental level, they are typically always either gravitational or electromagnetic. In Newtonian mechanics, we won't be seeing any type of force where the fundamental type of interaction responsible for that force is nuclear interaction or electroweak interactions. It will always be gravitational / electromagnetic. Okay. So we've already discussed about weight earlier today. And the weight of a body is given by the formula mg, and it acts vertically downwards, or as a vector, the weight is always pointing towards the center of the earth. Now let's talk more about contact forces. Okay. So let's specifically talk first about normal reaction, which we were already doing the other day. But now let's talk in more detail about normal reaction forces. Okay. So this is where we are back to topic in that sense. So you can start writing this part down if you want. But again, in my mind, you don't need to make very detailed notes about the theory points that we are discussing. Those notes will be available to you. What I want you to concentrate more right now is understand the theory parts. And then when we are doing numerical problems next, and when we do, vector analysis of forces and all that, those things I would like you to do the steps yourself. Any numerical problems that I'm solving, that I would like you to do the steps yourself on pen and paper. You need not make fair notes. You can just do rough steps yourself right now, and you can fair the notes later, or you have my PDF notes. You can keep those as the fair notes. But it's important that you practice the mathematical steps. That's the more important thing in terms of writing down. So that's why I told you not to write down the earlier part we discussed today, because that's just general information. You will have that in your PDF notes anyway. Okay, so having done the discussion about the fundamental forces, which is more about your general knowledge, now we are coming back to the topic of Newtonian physics or Newtonian mechanics. And in that, now we'll again talk about the common forces. So the first of the common force is weight. I'm not going to discuss more about that because we've already understood about weight. But next we'll talk about normal reactions, and then eventually we'll talk about tension. We'll talk about both these forces today. Yes, tensile force is actually the proper name for it. Tension is like a short form for it. Okay? Tensile force is the proper technical name for a force that acts along a rope or a thread when it is having a tendency to get stretched. Now, when external forces are acting on it in such a way, it gives it a tendency to get stretched. Then the kind of force that acts along the length of such a material, which is having a tendency to be stretched, that is called the tensile force, or tension in short form. We just call it tension. Okay. Tensile strength bit as something else. Okay, Ayush, tensile strength is a property of a material. It is to do with the fact that any material can experience up to a certain amount of limit of tensional force. If the force exceeds a certain limit, if the tensile force acting within a rope or a string exceeds a certain limit, then it will undergo a fracture, it will break. So that is to do with tensile strength. Yeah. So coming back, we have done in the last class, but let's talk more in detail. So coming back now about normal reaction contact force. So normal reaction is the type of contact force that we saw acts normal or perpendicular to the plane of contact. Okay, so it's a type of contact force that acts perpendicular, और in geometry perpendicular को ही हम normal कहते हैं. So it acts perpendicular or normal. Normal means perpendicular in this context to the plane of contact between two surfaces. Okay. Now, very important. Normal reaction is what we call a self-adjusting type of force. That means it adjusts itself in value, that is magnitude and direction, according to the external forces. Okay. It's a self-adjusting type of force. So let me explain what I mean by self-adjusting through some examples. Okay. So example 1 to understand that normal reaction is self-adjusting is this, that suppose we have kept a block of mass 5 kilograms, okay, on a horizontal surface. This is kept on a horizontal surface. And we take the value of acceleration due to gravity as the approximate value 10 meters per second. Now if I ask you in this example, how much is the normal reaction? Denoted by the symbol N, okay, on the block, okay, applied by the floor. So the answer is very simple. Right? It's equal to mg. Right? It's equal to 50 newtons. Correct? Okay. So we will understand that on the block there are two forces which are acting. Okay. On the block there is the gravitational pull of the earth, mg, or the weight, which in this case will be 50 newtons. Now this is pushing the block against the floor. So on the floor, the block is applying some kind of normal force like this. So the floor is applying the reactional normal force to that. So this one and this one here are the action-reaction pair. This is the force on the floor applied by the block. And this one is the opposite of that. This is on the block applied by the floor. So this normal reaction in this diagram, the one which is shown on the block, and this normal reaction in this diagram which is on the floor applied by the block, these two are the action reaction pair over here. Okay. Now, however, we know that the block is at a state of rest. Okay, so it's at rest means its acceleration is 0, its momentum is 0. So rate of change of momentum will also be 0. So by application of Newton's second law, this will show us that the net force acting on it should be 0. So in other words, the vector sum of normal reaction and the weight should be 0. But they are opposite over here. So that means when I convert this to a scalar equation, it becomes N is balancing mg. So the magnitude of the normal reaction is 50 newtons and it's acting upwards. Okay. Now let me show you what I mean by saying that it's self-adjusting. अभी देखो यही example में if I make a change like this where now next what I'm doing is the same situation. You have that 5 kg block resting on the floor, but in addition to that, I'll give you time to write it. I'll give you time, but that's a very trivial example. Okay. Now the same thing, the 5 kg block is lying like this, but additionally, what is happening now? Some external agent is also pushing the block against the ground with the application of some additional force. Okay. So there is an external agent now who is additionally applying a force of, let us say, some magnitude. Let's just say for argument, this force is of 20 newtons magnitude. Okay. So what's happening in this picture now is that an external agent pushes the block down, that is vertically downwards, with a force of magnitude 20 newtons. Okay. So now find the normal reaction. On the block applied by the floor. Okay. So now compare the two situations and tell me यहाँ पे क्या हो गया, normal reaction कितना हो जाएगा in the second case? It will increase to 70 newtons. Okay. So you can see now it's self-adjusting. On the other hand, the weight is not self-adjusting. मेरे external agent ने push किया, pull किया, weight को से कोई मतलब ही नहीं है. The weight will remain mg of 50 newtons vertically downwards. But depending on the other situation now, that in addition to the weight, I've also applied a downward force on this block. The normal reaction adjusts itself to balance so that the block remains in equilibrium. So that is what we mean by saying that normal reaction is self-adjusting. So in this diagram now what will happen is, in this second example, when you look at the complete force picture, mg is acting, which is of 50 newtons. Okay. But there is also this additional pushing force, which is pushing the block against the floor below with a magnitude of 20 newtons. So what is happening? The total force with which the block is pushing against the floor is increasing as a result of that. So the normal reaction that the floor is applying is in the vertically upward direction, but again it's such that the acceleration of the block is zero because it is at rest. So इस acceleration को zero करने के लिए normal reaction को adjust करना पड़ेगा ना. If the normal reaction here was still 50 newtons, then the net force would have been downwards. This 20 Newton force would have gone unchallenged. It would have gone unbalanced. So who adjusts for that application of that external force is the normal reaction that adjusts. So the net force on this block has to be zero again. So that is what is telling us that N is now balancing the sum of mg plus F. Okay. Because you can see over here that when we do the vector sum of normal reaction, weight and F. So this is normal reaction acting in the positive direction upwards, but mg is acting downwards. So we'll have to put it with the minus sign. F is acting downwards. So this sum is zero. So that is what is telling us that the normal reaction has therefore increased. To how much? It has increased to 70 newtons. So that is an example of how the normal reaction is self-adjusting. Okay. So now write down these two examples in detail. Okay. The left one is obviously a very trivial case, but it's just to show you that in the trivial case, if I create some external change because of some external agent, which is the one which adjusts itself according to the change I am creating, out of weight and normal reaction, weight is not going to adjust itself. Weight will be what we call an invariant force. Weight only depends on the mass of the block and the situation it is in, which is it's on the Earth's surface. So unless by some magic we are changing the mass of the Earth or we are compressing the radius of the Earth, it's not going to, so that's not going to happen. No? The Earth will remain the way it is. So accordingly, the weight of that object will not change. It will remain invariant. But which is the force which can adjust itself according to some external effect, and that is nothing but the normal reaction force. That's the one that adjusts itself. Okay. So this is the nature of normal reaction, that it is self-adjusting. Okay. So just make a note of this example, then I'll show you more examples of the self-adjusting nature of normal reaction. No, it's an actual force. No? Generally, it's not an assumed force, it's an actual force. Normal reaction is actually acting on the body. It's a physical force. It's an interaction between two surfaces. It's a contact force. Yes, there is a limit to normal reaction. But for example, suppose here the surface that I'm talking about is, let's say, a wooden board or something. Now that will also have a breaking stress. Na? So if my external force ko jo F lagaya hu main vertically downwards, if I now gradually start increasing it, at some stage I'll realize that either the block will break or the floor will break. So yes, there is a limit to the amount of normal reaction, And Aman, no, the normal reaction will not be 30 newtons. And the explanation of that is there in the diagram below. I'll show it to you again. You have to do the proper vector analysis. So you'll realize that F is increasing the normal reaction here because I'm pressing it down. So it's going up from 50 to 50 plus 20. No, normal reaction doesn't necessarily always act opposite to weight, Asmi. But yes, in the case where the surface is horizontal, जहाँ पर भी surface of contact horizontal है, वहाँ पे normal reaction vertical हो जाता है. Yeah, I'm showing you, Aman, don't worry. So the sum of these three vectors has to be 0 here, no? So a proper vector diagram for the fact that net force is 0 would be like this, that mg is downwards. We represent with proper arrows. mg is a 50 Newton arrow pointing downwards. The external force F that I have applied from top, that is also downward arrow, but of 20 Newtons. Okay. So if the net force is 0, the third arrow has to be vertically upward such that it brings you back to 0. No? So it has to be like this now. The third arrow has to be the normal reaction which balances the sum of these two downward forces. No? So this normal reaction will have to become how much? It will have to become 70 Newtons. So that what is happening? So that this thing is happening. The vector sum of these three is 0. This is where your vector analysis comes in. And yes, whenever we have a horizontal surface, you can say that yes, normal reaction will be opposite to it. It will be acting downwards. But if you have an inclined surface or a curved surface or something like that, then that effect will change. So as far as direction of normal reaction is concerned, it's basically according to the name. It's normal. It's perpendicular to the plane of contact. So it doesn't actually depend on weight in that sense. It depends on the plane of contact. Okay, so I hope this second example is clear to all of you. Why the normal reaction has increased from 50 to 70 Newton. This is very, very important to understand this. Yes, we'll take examples. Don't worry about that. We'll take. So another example I'll show you where normal reaction is self-adjusting itself. So hope this is clear, people. Yeah, of course, better. Normal reaction on the block will apply upwards only. No? The block is pressed against the floor. So how the floor is reacting? It will apply reaction upwards. No? So Aman, isn't it? It should be obvious to you, no, that normal reaction is upwards, better. Okay. Now let's see another interesting situation. The self-adjusting nature of normal reaction. Now suppose this whole experiment that we're doing of the block kept against a floor, this is inside an elevator. Okay. And the block is kept on the floor of the elevator. So this block is again 5 kg. And the elevator is going upwards. Sorry, it's just going upwards, not necessarily accelerated. So we'll discuss all the cases. Okay. So now the question is saying, take G equal to 10 meters per second square. Okay. Calculate the normal reaction applied by the floor of the elevator on the block as the elevator moves up vertically upward with. Now in case 1, uniform velocity. Okay. Case 2, uniform acceleration of 2 meters per second square. And third case is going up but with uniform deceleration of, let us say, 1 meter per second. So this you can relate to every day. Now, when you get into an elevator and you press a button for the top floor, you are at the ground floor, the elevator actually starts moving up, and initially it has some upward acceleration. Then as it achieves a stable speed, that acceleration becomes zero, so it's going up at constant velocity. Then again, as you come towards the floor where it has to stop, it has to decelerate, so it decelerates. So this actually happens when you step into an elevator. All the three things happen. It accelerates for some time, then for some amount of time it moves with uniform velocity, and for some amount of time then it has a deceleration. Now, the only thing in real life, the acceleration and deceleration may not be uniform. It might vary with time. But here we are assuming that they are uniform and their values are so much. So now just apply Newton's second law in each of the cases and figure out how much the normal reaction is. Okay. So I wish this is going to be an example where there will be a situation where there is some acceleration involved. Okay, the second and the third case, there is some acceleration involved. You'll see how normal reaction acts in a case when it's acting on an accelerated body. Yes, obviously the first case is 50 newtons. That's correct, beta. Now tell me second and third case kitna ho raha hai accordingly. Second case is not correct, beta. Yeah, Dhruv, your second case is correct. Parikshit, you have to understand the direction a little more carefully. Okay, so I'll give you the answers first, then I'll show you the explanation. So this case, the normal reaction will be 50 newtons. This case, the normal reaction will increase to 60 newton, and in this case, it will actually decrease to 45 newtons. So let's understand each of the cases now. Yeah, Dhruv, you got it correct. Many of you got it correct. Tanish, your second part is correct. Dharmil, you got it correct. So anyway, let's understand each of the parts. So in the first case, when you consider the forces acting on the box, there are only two forces. But more importantly, its acceleration is zero because it's going at uniform velocity. So acceleration is zero means that again when we apply Newton's second law, the net force should be mass into acceleration here because we're talking about a rigid body. So rate of change of mass, remember, is mass into acceleration. So that will become zero over here. This is the important thing. We have to apply this. Okay. So anyway, for net force, we need to understand what all forces are acting, and that is very simple. The forces acting here are only two forces. There is gravitational pull of the earth, and there is the normal reaction that the floor is applying on it, which is upwards. So the two forces acting on it are normal reaction and weight. So here the fact that net force is zero means plus m minus mg, because that's acting upwards, is zero. So the normal reaction has to balance the weight. Its magnitude has to be equal to the weight, so it has to be 50 newtons. So this is nothing different from the last case. The fact that it's inside the elevator which is going up makes no difference whatsoever because the elevator is going up with uniform velocity. It's not going up with acceleration. So that's why the first case is no different to when the elevator would have been stationary. Okay, this is the block, by the way, this is not the elevator. There's a mass of 5 kg. Yeah, so you got it now, no? Okay. Now the second case, if you look at it, what is happening is this box which is inside the elevator is going up with an acceleration of 2 meters per second square. So that's why when I look at the box individually, when I look at the block individually and consider the forces acting on it, this thing here, its mass is 5 kilograms, but it's having an upward acceleration of 2 meters per second square. And again, what are the forces acting on it? The same two forces, but this time it has to be pushed upwards. The forces are not balancing. In fact, there is imbalance. The upward force has to exceed the downward force. Okay, so my net force has to be mass into acceleration. So I can write in scalar form where upward direction is positive. So in that sign convention, n will come with positive sign, mg will come with negative sign, but this is equal to ma with positive sign because it's going upwards. So the normal reaction has to be having a magnitude of mg plus ma. So the normal reaction will become 60 newtons. So because the block is accelerating upwards now, so this pushing force has to be larger than mg. What is pushing it upwards is a normal reaction. It has to exceed the weight. That's the concept over here in this case. So hope it is clear to all of you why in this case the normal reaction exceeds the weight. It becomes mg plus ma. And based on this, now you can figure out the third case yourself, why it is becoming less than the weight. Okay, people, so hope this is clear. Correct, Asmi. Now the third part, now it's still going up, but it's going up with deceleration. So in the third part, the elevator has the upward motion. That means its velocity is upwards, but it's decelerating. That means what is the direction of the acceleration vector? The acceleration vector has to be downwards. Okay. So that is why the block inside it, when we understand its diagram, or when we look at its state of motion and the state of the forces acting on it, its motion is in the upward direction, but its acceleration vector will be pointing downwards. And that is given to the question as 1 meter per second square. Okay. And the mass of the block is given as 5 kg. So again, there are two forces acting on it, but this time, because it is having a downward acceleration, normal reaction is not able to balance mg. It's less than mg. So that the net force is downwards. So as you can see in this diagram, my force equation net force is equal to mass into acceleration. If I use the same sign convention that upward is positive, then ये net force कैसा हो जाना चाहिए? It should become minus ma because the a is downwards. When I convert this to a scalar equation, it should become minus. So plus n minus mg should become minus ma because I'm using this sign convention. This is using sign convention that upward direction is positive and downward direction is negative. But I need not do that. Okay, I can reverse the sign convention also. I can take downward direction as positive, then this will become mg minus n is equal to ma. So that also you can note. For sign convention, where I'm taking downward direction as positive. So in that situation, this equation will become like this. Become plus mg because mg is in the positive direction, minus n because n is in the negative direction, is equal to plus ma. In this sign convention will be written like this. But now you can see that there's no difference between the equation on the left and the equation on the right. This equation will give you the same value as this equation. It's just a matter of multiplying the whole equation with a minus sign because you are reversing the sign convention. Okay. So normal reaction either way, whether you go with this or this, it will become mg minus ma over here. And here because a is not 2 anymore, a is 1, so it will become 50 minus 5, or the normal reaction will become 45 newtons. Okay, people. So it's very important that you are able to implement Newton's second law correctly with the sign convention. So whether you use the sign convention where upward is positive or negative is positive, it doesn't really matter. It's one and the same thing. It's just two ways of expressing the same thing. So I used to answer your question. अगर average normal reaction पूछा है, तो then we'll average it out. But अगर instantaneous पूछा है, so it means at a particular instant. So at the instant when the elevator is accelerating, it is 60 newtons. At any moment while it is decelerating, or at any instant while decelerating, is 45 newtons. And at any of the instants when it's going at uniform velocity, it is 50 meters per second. 15 newtons. You understood the point better, Ayush? So typically in Newton's law chapter, we are not so concerned with the average value of force. We typically write Newton's second law in context of instantaneous equation. That at that instant the net force is so much when the instantaneous acceleration is so much. Unless a very specific type of question is asking you for average force, we by saying that how much is the force, we always mean instantaneous force. Now, the default meaning is that we are talking about the instantaneous value. Okay. Now let's see another more interesting example of normal reaction. So in my next example, I have this kind of thing. I have an inclined plane and a vertical wall. Like this. So both are fixed. There's a fixed wall and a fixed inclined plane. This is just the imaginary horizontal line. There's no such horizontal surface. So the inclined plane is fixed against the wall like this. So both are smooth, frictionless. Now this inclined plane geometrically is at theta equal to 37 degrees with respect to the horizontal. Acceleration due to gravity vector is like this one. Now we have a cylinder which is resting. Oops, just a moment. Too many cylinders. Just need one. Okay. So the cylinder is resting like this. So I have this cylinder which has a mass of 20 kgs like this. So find the magnitudes of the normal contact forces acting on the cylinder due to the wall and due to the inclined surface. Okay. Now we are coming to that kind of situation where our vector analysis is more complex. Okay. So again, you will see that this is the cylinder is resting over there. That means it's in equilibrium. Again, it's in equilibrium. That means net force should be 0. But unlike the previous case, how many forces are acting on the cylinder? This time you see there are 3 forces. It's in contact with 2 surfaces. So there are 2 contact forces which are normal, and the third one is the weight. So we have to apply that condition where the vector sum of 3 forces is 0. So now, having said that, the next question that will come to our mind is what is the direction of the normal reactions? So for that, the guideline is from the name of normal reaction only. It's normal or perpendicular to the plane of contact. So let's understand the plane of contact business over here. So let me draw this in more detail now. So because it is smooth, there will be only one type of normal contact. I mean, there will be only one type of contact force, which is the normal one, friction. Okay. We will come to friction after quite some time. Okay. We will discuss various situations of Newton's laws where all surfaces are frictionless. Then we will come later to a situation where we will deal with surfaces which are rough. Yes. Yes, Nikita, I'll verify your answer. Seems to be correct. Okay. In the meantime, let me try to be as accurate as possible with my diagram. तो अभी देखो contact जो है, it's happening at 2 places ना. So the contact on the cylinder is happening at 2 places. Let's concentrate on that over here. Okay. So here the plane of contact is vertical. So the direction of the force should be in which direction? It should be perpendicular to that. So the direction of the force at the point of contact will be like this. It should be perpendicular to the plane of contact. The plane of contact is vertical. So the force should be normal to that. So it should be along the horizontal line. So if you continue this further, in a very proper diagram, it should actually pass through the center. Let me see if I can make that happen. So this force vector actually acts along a line which, when extended over here, actually pass through the center of the sphere. So this is N1, let's say. This is the normal reaction because of the wall. So it will act in the direction which is perpendicular to this wall. So it's acting, as you can see, this angle is 90 degrees. Now similarly, the other one is the floor over here. So the floor has to apply a normal reaction at this point, which will have to act now perpendicular to this floor. Right? So it has to act along this line. So the floor will have to apply a normal reaction, which is, for that let me remove this. we'll come back to the angle and all that. इस point पे ऐसा perpendicularly act करेगा, act like this. Has to act along some line like this. That is this normal. So where these two meet, that is actually the center of the sphere, center of the cylinder. This will be the center of the cylinder. So anyway, this normal reaction now let us say is N2. Okay, this is that normal. Of course, coming back here, in this diagram, this angle here, this angle is theta equal to 37 degrees. And the third force which is acting, very significant obviously, is the weight of the object which is acting vertically downwards. Remember, weight is not affected by anything else. Weight will always be towards the center of the earth. So the weight will act through the center of mass, but it will act vertically downwards. So these three are the forces which are acting, drawn in a lot of detail. So now the body is at equilibrium, it is at rest, or what we call equilibrium, meaning that acceleration of the body is 0. So the net force should be 0. Or in other words, if I do the vector addition of N1, N2 and Mg, that should result in a null vector. This is the situation that we have to solve here. Okay. Now let's come to the detailed geometrical analysis of this. Okay. So now something very important that you have to understand. Whenever we have a inclined surface which is at theta to the horizontal, because there are so many cases where we are going to discuss this, you better memorize this thing. Whatever kind of object we have here, whether it's a spherical object, vertical, I mean it's a block or anything like this, it will always experience normal reaction along a direction which is like this here. Okay. So that is along this kind of line. Where this is 90 degrees. Okay. So if you want to understand how that is oriented with respect to the horizontal or vertical, you just drop a perpendicular from here, from this point. Okay. So this forms 90 degrees here. So this angle will become theta. Okay. So in other words, this normal reaction that is acting at the inclined surface will always act at theta to the vertical. So remember this as a rule of thumb. Okay. It's very easy to remember it in this way, that for an inclined plane at theta with respect to horizontal, with respect to the horizontal line or horizontal plane, okay, the normal reaction N, okay, acts along a line which is at theta to vertical. If you just remember this simple concept, you don't have to figure out this geometry by this triangle every time. ये जो line है, जो normal reaction जिस line के along act कर रहा है, that will be at theta to the vertical. So when you draw a diagram showing the forces, just understand that this normal reaction has a vector. इसका direction कैसे होगा? It will be theta with respect to the vertical. This angle will be theta. Why? Because it's very simple. If you look at the inclined plane, it's at theta to the horizontal. Inclined plane is at theta to the horizontal. So this angle is theta here. This angle is 90 minus theta, or in other words, this angle is theta here. So that angle has to be theta. So this is the derivation of this concept. But just remember this as a simple rule of thumb. Because there are so many cases where we look at normal reaction that this should become automatic after a while for you. कि अगर inclined plane theta पे है to the horizontal, then the normal reaction is at same theta with respect to the vertical. Okay. So just keep in mind this fact over here. Then we'll solve this equation. The sum of these three forces is 0. We'll solve that next. But to solve it, we need the angle properly. We need to understand the direction of that N2. N1 is fine, it's horizontal, but that N2's direction we need to understand. So for that, just remember this simple rule of thumb. So now you can see that if you draw that type of vector diagram where you're just showing the forces alone, how are the forces looking? They're looking like this. N1 is horizontal, mg is vertical, and N2 is the one which is like this. Now, by this principle, N2 will be at what kind of angle? It will be at theta equal to 37 with respect to the vertical line. If I draw the three forces from a common origin, this is what I realize. N1, mg are like this, but this one is at theta equal to 37 degrees with respect to the vertical. Now apply the condition for net force to be 0, where we know that mg is how much? It is 200 newtons. This is the only information we have about force. The rest we have to figure out from which equation? From this equation. The fact that net force or the vector sum is 0. So now it's become a vectors problem. ना? आपको दिखाना है that इन तीनों force का resultant is 0. Okay. Where one of them you know is 200 newtons, and you know the other one is along the positive x direction, the other one is at theta like this, and while this one is along the negative y axis. So we'll have to apply vector algebra to understand how much n1 and n2 are. So there are a couple of methods we can use from vector algebra. The most common and obvious one is use component algebra. So n2 को आप components में break कर दो. Yes, so mg will become equal to n2 sine 37, and n1 will become equal to n1 cos 37, because this angle is theta, with the vertical. So do this properly now. Break this n2 into components. Give it a y component and give it an x component according to this angle theta equal to 37. Yes, so n2 will become 1000 by 3. Sorry, 1000 by 2000 by 4. Sorry, 1000 by 4. So 250 newtons. My mistake. N2 will become 250 newtons. Okay. So my next step is, in this diagram, I'll break N2 into components. So this N2, whatever its magnitude is, but it's at 37 degrees with respect to the vertical. Theta equal to 37. So when I break it into components, now these components will become so this component will be N2 cos theta. So that will be 4 by 5 N2. And this will be N2 sin theta. That is 3 by 5 N2, because theta is 37. And apart from that, what other forces are acting on the body? There is N1 acting because of the wall on the left, like this. And there is weight acting because of gravity, vertically downwards. And this is 200 newtons. See, the thing is, if I write in component algebra, yes, plus minus will come, but here the direction is already shown. So this is the magnitude of this component. So that's how much this. So that's the idea. Now, see, if I write in component algebra that way with I cap, J cap, then yes, I will write N2 vector as minus 3 by 5 N2 I cap plus 4 by 5 N2 J cap. And I'll write Mg vector as minus 200 J cap. And I'll write N1 vector as some unknown magnitude but along the positive x direction. But that's not necessary to do over here. You can write it that way if you want, but it's not necessary. Now in this diagram, I want to make the net force 0. Okay, so the forces should balance. F net is 0. So if I express this in component form, so components along x-axis, they should balance each other. So along x-axis, what is happening? N1 is along the positive x-axis, and 3 by 5 N2 is along the negative x-axis. So that should be 0. So that's equation 1. So this is, in a sense, what we're doing here is balancing the horizontal forces. Whereas the other one, you look at the components along the y-axis. So the vertical forces should balance. So along the vertical, there is one component of N2 which is acting vertically upwards. So that is plus 4 by 5 N2. And of course, gravity is acting vertically downwards. So this is 0. That becomes my second equation. So the whole point is I can come to these equations directly from the diagram. I can skip this step over here of writing them in component form. This is not really necessary. Okay, clear? Okay. So now see, solve the second equation first. So from equation 2, you're getting N2 is 5/4 of mg. So it is 5 of 250. So from that you're getting your answer that the wall is applying 150 newtons. This is by the wall, and the inclined plane is applying 250 newtons. By the inclined plane. Okay. And the directions are as shown in the diagram already. Okay. So, now gradually we are coming to that situation where you're understanding the full scope of application of vector algebra in Newton's laws. This whole chapter of Newton's laws is going to be solving this kind of vector relationship or this kind of vector analysis, whether or not the body is accelerating or it's at rest. Ultimately, the more important thing in solving the equation is the left hand side of Newton's second law, which is net force, okay, which is going to come by vector addition. Okay, so I'll just leave you to understand the diagrams from the beginning. So first of all, this diagram is very important here. The direction of the various forces. Just take a look at this one in more detail once. So in this, for example, this is perpendicular, this line. Yeah, this is the last problem. We are done. Yashwardhan, we are done with today's lecture. Okay. So now the three forces which are here, they have to balance each other. Their vector sum has to be 0. So to make that vector sum 0, I am converting the force diagram to this one. N1, N2 and Mg are shown with the proper directions, and then further I am resolving N2. So here in this diagram, N2 has been resolved. Okay. Taking our coordinate frame like this one, that this is our x-axis and this is our y-axis. Then see, Jenny, don't go by that formula-based approach. When I say it's the y component is sine theta, then theta kya hota hai? It is the angle with the x-axis, no? Now here you can see the angle with the x-axis is not this. So if you want to go by that strict formula-based method, then you will have to consider that for this force N2, your angle is this one. So then you will have to take theta as 90 plus 37. So that is 127 degrees. Okay. So that will give you this vector relation. So your x component will become N2 cos 127. So that's how you're getting minus 3 by 5. And your y component will become N2 sine 127. So that's how you're getting 4 by 5. But here you just use trigonometry. E angle theta, so you can see this base will be cos theta. And this side will be the perpendicular, so it will be sine theta. Understood na beta Jani? Yeah. So again, this sine theta, cos theta business you have to be very careful about. A couple of important things in this: the resolution, and before this, how to understand N2's direction itself. So for that, you remember this rule of thumb which we have written over here. This is very important. Okay, this thing. Very important, this part. Anytime we have an inclined plane, the normal reaction that applies on a body will be in this sort of direction. Okay. Okay, so people, with that we come to a conclusion of today's lecture. Just make sure that you do a revision of this last question very carefully. and the vector analysis and all. And also do the revision of the whole concept of normal reaction being self-adjusting through the 2 or 3 examples that we've done. Okay. All right, people. So that's it for today's lecture. Next week we'll continue with more analysis on Newton's laws, including understanding more about tensile force or tension apart from normal reaction. Okay. I'll give you a worksheet also to work out some questions based on this, but it's all basically going to be vector analysis. All this is going to be about vector analysis and nothing else. Okay, people, that's it from my side.